Welcome to another episode of the Breadboard Apprentice. In today's episode we are going to continue working on the clock module that we started last time. Today we are going to integrate a push button so that we can generate single pulses. And we will also be taking a look into how we can properly debounce these switches so that we make sure that we only generate single pulses when we push the button. There are multiple ways to connect a push button like this, and in this diagram is perhaps the most simplest way that I know of to connect or drive an LED using a push button. Here the push button is directly hooked up to our voltage source, and once you push the button, that will let the current flow in the circuit. And if we are looking at the voltage curve of such a graph, or the voltage over the LED in this case, what we see is that at time 1, when we push the button, we immediately go up to our 5 volts, and then when we let go in time 2 of the button, we go down to 0 again, and the LED turns off. So let's build this simple circuit and see it in action. We don't want to forget to use the limiting resistor here, since otherwise this will happen. Okay, so now we have built this circuit. Here the current will flow from our positive voltage through the button. When we push the button, it will flow through limiting resistor, then through the LED into ground. And indeed it works. However, this circuit is not perhaps the only one that we can think of, and another one that is going to be more useful for us later on in the circuit. So let's draw that diagram and have a look at this. Now if we instead have a look at this circuit, so when the button is not being pushed, there is no connection here, meaning that the LED on both terminals are connected to 5 volts. Since we are using a pull-up resistor on this side here, using a 10K resistor, both sides will be at 5 volts. However, once we push the button, then this spot or this point will be pulled low, meaning that the current will be able to flow through the LED and down to ground. And if we are taking a look at the voltage diagram on this side of the LED, we will have 5 volts until we push the button. Then it will go down to 0, and then once we let go of the button, then we will shoot back up, or we will be pulled up to 5 volts again. So let's build this circuit as well. And so now I have hooked it up correctly with the ground, and we can see that when the button is not pushed, then both sides of the LED is pulled to 5 volts. But as soon as I push the button, then this spot here over the push button, which is this spot here, is pulled low to ground. and the LED can turn on again. And this way of connecting the push button is this way to connect the push button is going to be much more useful for us later on in the build, as we will see later in the episode. Both of these voltage curves I have drawn as though all the components are ideal in the circuit. One of the components here, the push button, is far from ideal since there are some tolerances within the build and manufacturing, and once you're pushing them, usually what's happened is that there is some bounce between the connections, meaning that you will lose the connection for a brief moment before it can settle again and make a steady connection. And the same goes when you're releasing the button. It usually bounces a little bit there as well, so that it will not stay disconnected but actually make several connections once you let go as well. And here I have drawn out a voltage curve of such a situation. So it again starts off at 5 volts in this case, since we are pulled high. And then once we are pushing the button, we might go down to 0, but then as the bounces happen, we will shoot up back to 5 volts, and this can go on for quite a few bounces before it can settle down to be truly grounded. Then once we at time 2 let go of the button, then we can again see bounces happening before it actually turns off completely. Of course, as we saw before, we cannot really see this behavior ourselves, and that is because these bounces are of course very high frequency and very short pulses, so our human eyes will not be able to detect them. So what we can do to actually detect whether or not our button is bouncing, we can connect a digital component that counts the pulses. And I have here just such a circuit. This is an LS161, a 4-bit counter. So let's connect this one and see whether or not we can detect the bounces. So to start with, on pin 8 we have ground that we have connected, and on pin 16 we have a VCC, and on pin 9 we have the load button or the load pin, and that is active load, and since we will not be loading anything, we set that high. Likewise, we have ENP and ENT on pin 7 and 10, and those needs to be set high as well if we are to output anything. So next we will hook up the output. And we see all LEDs come on at once, and that's just because these chips, they don't have any deterministic state to come onto when they first boot up. Instead, it's quite random what is being stored once it starts. But we can always use our clear pin, which is pin 1, and that is also active low. So let's set that high. Okay, now we have connected this. So the way that these chips work is that they wait for a leading edge before they start counting. So they count every leading edge in a diagram, or they count every leading edge or voltage spike as when it's inputted. So remember now, if there is no bounces in the beginning, there should not be turning on anything, or it shouldn't count anything, since that's just a leading or a trailing edge. And now once we let go, then we should be able to count up once. But what we see is, of course, it counts multiple pulses. And now what we saw, even when we pushed down, we saw actually it count once. And when we let go, then we only counted once. So there were no bounce when we let go this time. And there we got a single pulse this time, and there we got another single pulse, and there we got two of them. So it's quite inconsistent, and we are not always getting bounces, but we really want no bounces at all. So let's think about how we can go mitigating these bounces that we see. One way to do this is with an RC network, and I have added this to the diagram that we saw before, or the schematic. And to create this RC network, I just added some components here. So I added a resistor, a diode, and a capacitor. Really what is needed is the capacitor, but to have the full benefits and the nicest behavior, we need to add the resistor and the diode as well, and I will explain these later when we take a look at the voltage diagram. But for now, just keep in mind, so when we supply power here, what's gonna happen is that the capacitor is going to start charging through the pull-up resistor, through our diode, and it's gonna be charged up to 5 volts. Then what's gonna happen when we are pushing our button? Well, then this point here, as we remember from the last diagram, is gonna be pulled to ground, meaning that our capacitor is gonna discharge through the resistor here and to go to ground. And if we take a look at the ideal version of the voltage diagram, thinking that the push button is an ideal, switch, meaning it will not bounce. And we start off in the steady state when the capacitor is fully charged at 5 volts. Then once we push the button, we're gonna see a voltage drop, but not instantaneous, since the capacitor is discharging through the resistor here that we added. Once it's fully discharged, then we're reaching 0. Then once we let go of the button, it's gonna slowly recharge again through the pull-up resistor and through the diode, and until it reaches our target voltage, or until it reaches the 5 volts. Now let's have a look at a real button, what's gonna happen when we see bounces. Well, now again, when we have a steady state, we see 5 volts. Then when we push the button at T0, we're gonna see that nice and slow voltage drop again. And if we have a bounce, then we are gonna have a small bit of charge going into the capacitor again. So we are increasing a slow amount or a low amount of voltage. And then once the button is released again, it's gonna start falling again. And this is going to keep happening until it stops bouncing and we go all the way down to 0 again. And what is notable here is that this capacitor, it acts to limit these voltage spikes when we have the bounces, so the effect will not be as big as it was before. And really, the size of these voltage spikes depend on the frequency or the time where we have the bounces, and also the values of the components that we are adding here. So in this case, we have a resistor of 10K and we have a capacitor of 1 microfarad. And to calculate the time or the time constant for this circuit, you just multiply the two resistors or the resistor and the capacitor together. So in our case, that means that we have a time constant of minus 10 to the minus 2 or 10 milliseconds. So let's try and build this circuit and see whether or not this is enough to mitigate the bounces. Okay, we have hooked up this circuit now, and let's test it out again. And what we see is that the circuit seems to be bouncier than ever, and this does not make sense immediately, since what I said was that this capacitor or this circuit would actually smooth out the voltage spikes and remove these. So let's have a look in the oscilloscope and see whether or not we actually obtain this curve. I had a lot of trouble hooking up the oscilloscope to capture these switch bounces, and I don't go into too much detail here in this episode, but if you want an in-depth explanation of all that went wrong when I was hooking this up, then I can make a separate video discussing all the things that I learned about the oscilloscope and how to actually take measurements using it. We see that this works in the direction of charging. So when we let go of the button, it works fine and everything seems to be working. The capacitor is charging at the rate we would expect. However, when we are looking at the discharging cycle, once we push the button, then this capacitor is discharging way too fast. So let's see if we can find out what is going on. So I have located the error, of course. This diagram is not quite all right that I drew before. But let's just see here that in the trailing edge now that we have, we can see that we drop off to So what we see now is that we are not going down all the way to 0, but we're staying at 1 volt, which is not quite enough for triggering any pulses. So let me see if we switch out this 10k resistor to a 1k resistor, if we can't bring that down a little bit. That looks much better. So now we see we do have a nice and slow descent, and we are going all the way, or almost all the way, down to 0. And we can have a look at with the cursors. So now let's just have one more look at the trailing or the leading edge in the end of the diagram and see. And here again we see a nice slow ascent, just as we would expect. So we had to make some changes to this circuit. First off, in order to bring the voltage back to under 1 volt, or bring it down low enough for us to count any pulses, we needed to change this resistor to a 1k instead of 10k. So why is the circuit bouncing still? And I feel that now is the perfect moment to talk about what ones and zeros are in computing. So as a programmer, I have never really thought about what 0 and 1 is. It's just that it's either 0 or a 1, and there is nothing really in between those two. In electronics, of course, we need to represent these values somehow. And naively, I thought first that, of course, a 0, then it's just grounded, and a 1, that's just the voltage at the circuit is operating at. So in our case, that would be 5 volts. However, that I have learned that that is not really the case. So for these circuits that I'm gonna use, which is from the LS and HCT series of the 74 logic family. We have defined some values that these chips operate at, and these are the voltage output high minimum, meaning that these chips will always output a certain voltage. And then we also likewise have a voltage output low maximum, that these chips will never output a low value or a zero above this voltage threshold. Then we have the more important things, the inputs to these chips. So the input high minimum voltage for one of these chips, the voltage where you would actually register a 1, is 2 volts. So anything above 2 volts would be registered as a 1. Then we go to the input low maximum, that is the voltage at below we will always register, or these chips will always be registering a 0, and that is not 0 volts but actually 0.8 volts. And that has this funny quirk with it, that the interval between these two voltages, the input voltage low maximum and input voltage high minimum, that region is undefined. So we don't really know what will happen if we receive a voltage like that into the chip. So it can either be a 1 or it can be a 2. Not a 2. It can either be a 1 or it can be a 0. And this is what I believe is happening to our counter. Now that we are slowing down the signal, or the leading edge, what is actually happening is that we are spending an excessive amount of time in this undefined region, where we likely will see some undefined switching between ones and zeros. So how do we actually deal with these fluctuating or these slow transitions? Well, one way is to use what's called a Schmitt trigger. And these are triggers, or these are circuits that include a sort of dead space. So instead of having this undefined behavior in the middle, the Schmitt trigger, what it does is, if you have an input here in green, as it goes up and it goes over a threshold, in this case 1.4, then the output will be switched or turned on. And then it doesn't matter if the input goes down a little bit, because this is a dead space, so it will not switch when it's in this region. It's only when it actually crosses the lower boundary that it will, in this case at 1 volt and typical at 8, that it will switch back again. And this is such a circuit. It is the 74 HTC 14, and it is a logical inverter just as the 74 LS04, but it also features a Schmitt trigger. And since this is an inverter, well, that is why we used this circuit before, when we used a pull-up resistor, so that we basically inverted and had a well instead of a bump or a pulse. So, and this is why we now, when we are hooking this up, we will get that pulse finally. And there we have it. So now, including this Schmitt trigger inverter, we are actually able to count using this button without any bounces. And that's great. That is all we had time for today. If you have any comments or questions about what we did today, be sure to leave a comment below. Bye!